Look at phase changes. Remember, on heating, a phase change might occur without a temperature change. That's called a heating curve. All right, so let's just take a system like this. And here we're putting in heat into the system at a constant rate. And let's initially we have, say, a solid. Let's look at a heating curve for this. Heating curve means what we have here, Q being put in at a constant rate. You keep putting in some heat. And let's look at how the temperature changes. So right here, we initially have a solid, and let's say that's initially at this temperature. As we put in heat, what will happen is that the temperature will go up according to, well, because of heat capacity. And if the heat capacity is a constant over temperature, this will just be a straight line. But where you find at a particular temperature, you're not putting in heat, the temperature doesn't rise. In fact, what you do here is here you are melting the solid. So all the heat that you're putting in does not go to increase the temperature, but is going to induce this phase change. Now when you put in enough heat so that all the solid is converted to a liquid, then you start increasing the temperature of the liquid. And then at a particular point, say at this temperature up here, all the heat you're putting in goes not to increase the temperature of the substance, but in fact it goes to a phase change. And here this is vaporization. And when you put in enough heat so that you converted all the liquid into a vapor, then the heat you put in starts to increase the temperature of the vapor. So these are phase transitions. This is the temperature of fusion. This is the temperature of vaporization. And we'll consider these in more detail when we talk about the second law of thermodynamics in the next lecture. So just a review of phase changes. Here's an interesting example. How does a rice cooker know when to turn off? So here's our rice cooker. And let's make a little steam vent up here and so on. Here's some water, and here is some rice. As this thing cooks, there's a heater up and down here, a rice cooker diagram, a rice cooker, not to scale. So you're heating the rice and the water. The water starts to boil. So eventually we're up here, and it's boiling at 212 Fahrenheit or 100 degrees Celsius if you're at 1 atmosphere pressure. And now eventually what happens is that the rice is now absorbs, this is the heater, and why am I doing that? Let's just get rid of that. There's the heater down here. And then eventually what you have just here is rice that's absorbed all the water. That's one process of doing rice. Now the heat that goes in here is going to increase the temperature of the rice. Before it was just doing that phase change, changing water to liquid water to vapor. But now the water is all absorbed, and now the temperature starts to rise up here. And so all you have to do is to have a thermostat or some sort of device that will shut water, shut off. This will be U, not an I. Shut off the heater when the temperature goes above 100 C. Oh, that's a useful application to these heating curves. Let's work on this example here. Calculate delta U and delta H when 1 gram of ice melts to 1 gram of water at 1 atmosphere and 0 Celsius. And we're given the density of ice, the density of water, the enthalpy of fusion of ice. Let's draw a picture. Here's our initial state. We have ice, which I'll just denote here as a solid. We said it's at 1 atmosphere. We have 1 gram, and it's at 0 Celsius. And now the final state, taking that to a liquid. We now have liquid. We melted the ice, and the problem states it's still at 1 atmosphere. We haven't added any water, so it's still 1 gram, and it's still at 0 degrees C. So that would be somewhere along this process here. So we're not increasing the temperature, and it's a constant pressure, so we have maybe a lid or something. Well, we might as well make this into our standard here. There's our piston, 1 atmosphere. And again, so any volume change will be done. Our piston here, 1 atmosphere. So any volume change will be against a constant pressure. Now, maybe you know that the density of the solid ice and liquid water are different. That's why, for instance, ice cubes float on water because the density of the ice cube is less than the density of the liquid. So when we go from here to here, we're going to have a volume change, which means there'll be some work done. What we're asked to calculate here is a change in internal energy and the change in enthalpy. This is a constant pressure process, so the change in enthalpy will be easy, delta H. This is just the heat, QP, a constant pressure. This process is a constant pressure process. So that's just equal to the heat transfer going from there to there. How do we calculate that? Well, we know the enthalpy of fusion of ice. All right, there it is, the enthalpy of fusion of ice. So if you take 1 gram of ice, and this is normalized, so this would be called the specific enthalpy of fusion of ice. 1 gram will take this many joule. Oh, look, we have 1 gram, so we can say that this is just, well, I'll just work it out, 333.5 joule per gram, and we have 1 gram, 333.5 joule. So that's the enthalpy change. That was a constant pressure process. To melt 1 gram of ice, we need 333.5. It's positive because we've got to put in Q here in order to melt the ice. Now let's look at delta U. Delta U, we recall, is Q. All right, there we already calculated the Q. However, there's a W, internal energy. And there we know that the density will be different in these two cases, so that there will be some, in fact, this is less dense, this is more dense, so there'll be a contraction here. Let's calculate W for this process. W is a constant pressure process, so we can just use minus P delta V. And let's see what the pressure is. The pressure is 1 atmosphere. But what is delta V? Well, that's why we're given the densities. Delta V is the final volume. That's the volume of the liquid, minus the initial volume. That's the volume of the solid. Final volume will just be the density of the liquid. Looking that up, that is, actually we're given that here. The density of the liquid, 999.84. 1 gram, divide by the density to get the volume, 0.99984 gram per milliliter. So the final volume is 1.00016 milliliter, ignoring significant figures here. The initial volume will be equal to, again, we haven't added or subtracted any water, so it's still 1 gram, but the density of the solid, the initial was a solid, is, as we said, a little less dense, 9168 gram per milliliter. So the initial volume is 1.09075 milliliters. So that delta V is the final volume, 1.00016 milliliters, minus the initial volume, 1.09075 milliliters, and that is minus, that'd be a minus sign here, minus 0.09059 milliliters. So that's the volume change when you melt ice, and so there would be a contraction in volume as we guessed. And now to find the work, we take that volume change and multiply it by pressure and take that minus sign. So that work now will be minus the pressure. Everything was at 1 atmosphere. The volume change we said was minus 0.09059 milliliter. And this comes out to be, well, that's kind of easy multiplication. The negative signs cancel out. 0.09059. And the units here are milliliter atmosphere. Let's change that into liter atmosphere, 9.059 times 10 to 3.5 minus 5 liter atmosphere. And we look up the conversion factor. We want to put in joule here. The conversion factor is 101.32 joule per liter atmosphere. And so this comes out to be 9.18 times 10 to the minus 3 joule. Well, that's not a lot of work compared to the enthalpy change, 333 joule. That's like 10 to the minus 3 joule added on to this. We're going to go ahead and do the calculation, but delta U is equal to Q plus W. Q was 333.5 joule, and W, kind of small, 9.18 times 10 to the minus 3, so to significant figures, 333.5 joule. So in this case, the work done is so minuscule that the change in internal energy, delta U, is, for all intents and purposes, the same as the enthalpy change. Okay, that's just an example of how to calculate, use first law, calculate things, phase change, difference between delta U and delta H.